SpaceX built a rocket designed to lose money on its first 100 launches, yet it is the single reason Elon Musk could become the world's first trillionaire. For over 60 years, going to space was the single most expensive endeavor in human history. Decades after Apollo, the space shuttle program promised routine access to the cosmos, only to rack up a staggering price tag of $54,000 for every single kilogram delivered to space. Today, NASA's flagship space launch system burns through over $2 billion every time it leaves the pad, only to be thrown directly into the ocean after just 8 minutes of flight. Imagine buying a brand new Boeing 747 airliner for $200 million, loading it with passengers for a single one-way flight from New York to London, and then crashing the aircraft into the Atlantic Ocean upon arrival. That sounds like complete financial insanity. Yet that exact business model was the foundation of the entire global space industry for 6 decades. Governments and satellite megacorporations accepted these staggering costs as an unavoidable cost of doing business. Then came a radical shift. Down in the remote coastal village of Boca Chica, Texas, a private company built a towering stainless steel skyscraper designed to explode the underlying economics of spaceflight once and for all. It is called Starship. On paper, Elon Musk has claimed that this colossal vehicle will reduce the cost of reaching orbit by more than 99%, bringing internal marginal launch costs down to a mind-boggling $2 million per flight. It is vital to separate SpaceX's internal marginal cost from the market price charged to customers. If SpaceX lowers its internal cost to $2 million while charging commercial satellite companies or NASA $15 to $20 million per launch, it creates an unprecedented 80 to 90% profit margin. Starship will not merely compete with existing aerospace contractors, it will generate unprecedented cash flow to fund Musk's interplanetary ambitions while utterly annihilating every other rocket operational on planet Earth. But beneath the hype, the viral launch videos, and the ambitious timelines lies a complex web of financial trade-offs, manufacturing bottlenecks, and extreme technical risks. To launch anything into orbit, a rocket must accelerate to roughly 17,500 miles per hour. Achieving that velocity requires an immense amount of energy, which means the vast majority of a rocket's total weight must consist of propellant rather than cargo. In traditional rocketry, every structural component, guidance system, and custom-engineered engine is treated as disposable packaging. When you break down the financial architecture of a traditional rocket launch, manufacturing expenses account for over 85% of the total cost. The actual propellant, the liquid hydrogen, kerosene, or oxygen burned during flight, represents less than 1% of the price tag. For decades, the entire aerospace sector was trapped in an absurd economic paradox. 99% of the money spent went toward hardware destined to end up as twisted metal at the bottom of the sea. This single constraint kept the global space market tiny. Only wealthy nation-states and multi-billion-dollar telecom conglomerates could afford to launch payloads. Because launches were rare, rocket manufacturing could never achieve economies of scale. Every single rocket was custom-built by hand over months or years, driving production costs even higher. It was a self-reinforcing financial trap. To break the cycle, someone needed to build a rocket that operated like a commercial airliner, one that could land, refuel, and fly again thousands of times. When SpaceX introduced the Falcon 9, the industry was deeply skeptical. By landing and reusing only the massive first-stage booster, SpaceX managed to cut launch costs down to roughly $1,500 per kilogram. This single innovation allowed SpaceX to capture a dominant share of the commercial launch market. But Falcon 9 was only a partial solution. The upper stage of the rocket, the second stage carrying the payload into final orbit, is still thrown away on every mission. That disposable upper stage alone costs around $10 million to manufacture. While Falcon 9 proved that partial reusability works, it also revealed a hard economic ceiling. As long as any portion of the rocket is discarded, the marginal cost per launch cannot drop below the cost of manufacturing that discarded piece. To achieve true mass-market access to space, SpaceX had to attempt what every major aerospace legacy contractor considered impossible: full, rapid, and total reusability of both stages of the Super Heavy launch vehicle. Enter Starship. Standing nearly 400 feet tall, Starship is the largest and most powerful flying machine ever constructed. It consists of 2 distinct components: the Super Heavy booster at the bottom, equipped with 33 engines, and the Starship spacecraft at the top. Unlike any rocket before it, both components are designed to return to the launch pad, be caught by giant mechanical arms, and be prepped for another flight in a matter of hours. If SpaceX achieves this vision, the financial equations governing space access undergo a seismic shift. Instead of writing off a $100 million asset on every launch, the capital expenditure of building the rocket is amortized over hundreds or even thousands of flights. Under this operational model, manufacturing costs fade into the background. The dominant expenses suddenly shift to marginal operational costs: propellant, launch site maintenance, ground crews, and insurance. Let's look at the raw numbers behind a single Starship launch. The vehicle burns a mixture of liquid methane and liquid oxygen, collectively known as methalox. Liquid methane was chosen specifically because it is cheap, clean-burning, and leaves minimal soot inside the engines, allowing for rapid reuse without exhaustive overhauls. A full propellant load for the combined Starship stack requires over 4,600 metric tons of fuel. At current industrial market rates, purchasing this massive volume of liquid methane and oxygen costs between $500,000 and $1 million. Add in the cost of electrical power, logistics, and pad operations, and the direct cost of supplying a single flight comes out to around $1.5 million. If SpaceX can scale operations to the point where maintenance costs per flight are kept under $500,000, the true internal marginal cost to fly Starship really could sit near the theoretical $2 million mark. Dividing $2 million by Starship's baseline payload capacity of 150 metric tons yields an internal cost of roughly $13 per kilogram to low Earth orbit. Compare that to the $54,000 per kilogram of the Space Shuttle era, or even the $1,500 per kilogram of Falcon 9. Even when SpaceX charges external customers a retail market price of $20 million, or $133 per kilogram, it still represents a price reduction so severe that it redefines what is economically viable in space. However, achieving those theoretical low costs is not just an engineering problem, it is a brutal volume problem. To understand why, you have to look at how fixed overhead costs interact with launch cadence. SpaceX has invested over $15 billion into developing Starship, constructing the vast Star Factory infrastructure in South Texas, building orbital launch towers, and hiring thousands of top-tier aerospace engineers. If Starship flies only 10 times a year, the fixed costs of maintaining the facilities, paying the workforce, and amortizing that multi-billion-dollar development budget get spread over a tiny number of missions. Under a low-frequency flight schedule, the effective cost per launch explodes to well over $50 million, instantly destroying the economic thesis. For Starship's unit economics to work, the rocket cannot simply fly occasionally. It must fly hundreds of times every single year. This requirement creates a massive strategic predicament. Where does all that demand come from? Currently, the entire commercial launch market on Earth only demands around 100 orbital launches per year across all rocket providers combined. Even if SpaceX captured 100% of the global commercial satellite market, it would not provide enough flight volume to justify Starship's operational infrastructure. To solve this demand crisis, SpaceX did something no traditional rocket company had ever dared to do. They created their own customer. That internal customer is Starlink, SpaceX's satellite internet mega constellation. Building and maintaining a global satellite network requires launching thousands of heavy, low-Earth orbit satellites every few years as older hardware deorbits and turns into atmospheric dust. Falcon 9 can carry roughly 23 next-generation Starlink satellites per flight. Starship, with its massive 9-meter payload bay, can deploy over 50 massive Starlink 5.2 satellites in a single launch. By using Starship to build out the Starlink network, SpaceX effectively subsidizes its own launch cadence. Starlink generates billions of dollars in recurring subscription revenue from millions of users worldwide, which in turn pays for the ongoing operational costs of flying Starship. The rocket enables the constellation, and the constellation funds the rocket. It is a closed-loop economic flywheel designed to keep launch rates absurdly high. Yet even with Starlink driving demand, Starship faces a massive financial roadblock that could derail Elon Musk's ultimate vision. Without an orbital gas station, every Starship lunar mission instantly turns into a $500 million financial nightmare. Launching cargo to low Earth orbit just a few hundred miles above the surface is relatively straightforward, but Starship was not built just to circle Earth. Its ultimate mission is to carry heavy payloads to the Moon for NASA's Artemis program and eventually build a permanent human city on Mars. Here is where the cold equations of orbital mechanics threaten to shatter the business model. When Starship reaches Earth orbit carrying 150 metric tons of cargo, it consumes almost all of its onboard propellant. To leave Earth orbit and head toward the Moon or Mars, the spacecraft must be completely refueled in space, Refueling Starship in orbit requires launching multiple specialized tanker versions of Starship, each carrying hundreds of tons of liquid methane and oxygen into space, docking with the primary spacecraft, and transferring the super-chilled cryogenic propellant before it boils away in the heat of the sun. To send a single crewed Starship to the moon for NASA, SpaceX will need to launch anywhere between 10 and 16 tanker flights just to fill the tanks of that one lunar lander. Suddenly, a single lunar mission is no longer one launch. It is a complex logistics train of over a dozen rapid launches in sequence. If even one tanker launch suffers a delay, or if cryogenic fluid transfer in zero gravity proves inefficient, the operational cost of deep space missions escalates exponentially. Instead of costing a modest internal baseline, a single mission to the moon could easily cost dozens of millions of dollars in unexpected operational overhead. Furthermore, manufacturing the rocket engines at scale represents another hidden financial vulnerability. The Super Heavy booster relies on 33 Raptor engines firing simultaneously, while the upper ship uses another 6. That means every full Starship stack requires 39 high-performance rocket engines. For context, legacy aerospace companies often took years to build a single engine costing upwards of $50 million. SpaceX has re-engineered the Raptor engine for automotive-style mass production, bringing manufacturing costs down to roughly $250,000 per engine. But with 39 engines per vehicle, a single catastrophic explosion on the launch pad destroys nearly $10 million worth of engines in a fraction of a second. This risk is not theoretical. During early test flights, the incredible acoustic energy and raw force generated by 33 Raptors destroyed concrete launch pads, throwing debris for miles and causing millions of dollars in unexpected infrastructure damage. To fix this, SpaceX had to design and install a massive steel water deluge system to protect the pad. Every repair, delay, and redesign drains capital from the company's reserves. Yet despite these extreme technical hurdles, the broader economic fallout of Starship is already being felt across the entire aerospace industry. Legacy defense contractors and international space agencies built their business models around selling expensive, disposable rockets for $60 to $100 million per launch. Companies like Aerospace in Europe, United Launch Alliance in the United States, and state-backed space programs in Asia are suddenly facing an existential crisis. If Starship achieves even a fraction of its performance targets, traditional commercial launch vehicles will become financially obsolete overnight. Customers will no longer design tiny, ultra-expensive, lightweight satellites out of rare materials to fit onto small rockets. Instead, Starship's immense cargo volume will allow companies to build cheaper, heavier satellites using off-the-shelf industrial components. The entire satellite manufacturing supply chain will be forced to pivot from expensive aerospace precision to mass industrial production. If you zoom out from individual launch metrics and evaluate the total addressable market, Starship is fundamentally a bet on the creation of an entirely new orbital economy. Today, space is used primarily for two things: Earth observation and telecommunications. It is an information-based economy. Starship aims to convert space into a physical, industrial economy. Consider in-space manufacturing. Certain advanced materials, such as ultra-pure optical fiber, complex protein crystals for life-saving pharmaceuticals, and defect-free semiconductor wafers, can only be manufactured in zero gravity, where convection currents and buoyancy forces do not disrupt chemical bonds. Currently, manufacturing these materials in orbit is financially unfeasible because getting raw materials up and finished products down costs thousands of dollars per kilogram. At a transport cost of $100 per kilogram, zero-gravity manufacturing plants suddenly become wildly profitable. Multinational pharmaceutical giants and microchip manufacturers could begin renting cargo space on orbiting Starship factories, producing high-value goods in space and sending them back to Earth via heat-shielded re-entry capsules. Then there is the concept of orbital data centers. As artificial intelligence models demand unprecedented amounts of electricity and cooling, terrestrial data centers are straining power grids and water supplies across North America, Europe, and Asia. In low Earth orbit, solar panels operate at maximum efficiency without cloud cover, and cooling can be achieved via radiative dissipation in the deep vacuum of space. Starship's immense capacity could allow big tech companies to deploy nuclear-powered or mega-solar AI compute clusters into orbit, bypassing terrestrial power grid constraints entirely. Yet, despite all these world-changing possibilities, the timeline for this economic revolution hinges on a single, brutally difficult engineering milestone: achieving true rapid reuse without refurbishment. If SpaceX is forced to spend weeks inspecting, repairing, or replacing thermal heat shield tiles on the belly of Starship after every atmospheric re-entry, the vehicle will suffer a crushing financial setback. SpaceX engineers are currently locked in a relentless battle against physics to ensure Starship's heat shield tiles can withstand 5,000-degree atmospheric re-entry temperatures over and over again with zero human maintenance. If the heat shield fails to achieve true airliner-like turnaround, the dream of $2 million spaceflight dies instantly. So, what is the ultimate verdict on Starship's economics? Is Elon Musk's mega rocket a brilliant financial masterstroke or an overhyped money pit? The answer lies in understanding that Starship is not just a product, it is an economic bridge. In the short term, the vehicle will be heavily subsidized by SpaceX's booming commercial launch business and profitable Starlink constellation. The initial launches will certainly not cost $2 million. They will likely cost SpaceX between $30 and $50 million as they refine thermal shields, master orbital refueling, and scale up launch tower catches. However, unlike legacy aerospace contractors who operate on fixed cost-plus government contracts that reward inefficiency, SpaceX has engineered a business model built on ruthless iterative cost reduction. Even if Starship only achieves 10% of its ultimate economic targets, landing at an internal cost of $1,500 per ton instead of $13 per kilogram, it will still be radically cheaper than any other launch vehicle in human history. For decades, the global space industry was constrained by a brutal economic catch-22. Space was too expensive because nobody was going, and nobody was going because space was too expensive. Starship breaks that cycle by brute forcing high flight volume, total reusability, and automotive-scale manufacturing. It replaces the boutique craftsmanship of legacy aerospace with the cold, unstoppable efficiency of modern mass production. Starship doesn't just lower the cost of space, it forces us to ask, if reaching orbit becomes cheaper than air cargo, who will actually control the supply chains of the modern world?